Okay, start recording. Get rid of this.
Only one class you'll be able to take in the spring?
I don't think there's any other questions.
Okay, guys, if I can get your attention, I'm going to start out with a quick review. Okay, first thing I'm going to start out with is confidence intervals. Right, very quick review of confidence intervals. Okay, so we know that we're interested in knowing what the mean, the middle value for a population is, the mean, the center of the values for a population for a numerical variable. We're also interested in how spread out the values within that population. We call the mean, the numeric mean, the average, call that mu for a population. We also call that a parameter. And for the standard deviation, a measure of the spread, we use sigma for standard deviation of a population. When we're dealing with a sample, we use X bar and we use S, for instance, S, SD, and so on. So, but some sort of English notation. Okay, so this is the mean of a sample, standard deviation of a sample. Okay, they're very different, right? What we're really interested in, we don't take when we have a population of 1 million people, right? We're not interested in taking a sample of size 100, taking some random sample of those 100 from those 1 million people and getting an average for that sample. We're not really interested in the average of that sample. We're really interested in the mean for the population. But since it's not practical to go and measure everybody in the population, the closest that we're ever going to get is by taking a sample. The bigger the sample, the better. The more representative it's probably going to be of the population mean. So X bar is a tool for us to get to the population mean, okay, or estimate the population mean. Okay, so X bar approximates the mean of the population. Okay, similarly, most of the time, we're not going to know what the spread of the population is any more than we would know what the mean of the population is. So for that, we use the standard deviation of those 100 people of that sample that we took as well. Okay, and because it's a sample from the same population, the standard deviation of the sample also approximates the standard deviation of the population. Right? They're just a way for us to measure what the standard deviation of the sample is. Now we go a step further. Since we're working with samples, we want to understand how repeated samples behave. In other words, if I took another sample of 100, another sample of 100, would that help me estimate what the true population mean is? I wouldn't get the same. It's kind of confusing. Ever hear the expression that the man who has 2 watches never knows what time it is? If I take the sample twice, I'm never going to get the same number. I don't know which one is closer to the mean or not closer to the mean. Well, now what if you take the sample 1,000 times? You got 1,000 watches. Well, the best you can say is that now I see a new range for the watches that I have, right? Because I've taken another sample, and we can start to understand how the samples of that size would be spread out, and we call that the standard error. That's the standard deviation, the spread for all the sample means, for all the X bars, right? So the standard error is equal to the standard deviation of the population over the square root of the sample size. I just mentioned that very rarely do we know the population standard deviation. So very often we have to use an approximation and say the standard deviation of the sample over the square root of the sample size is what our standard error is equal to, right? Because it's practical. It's just practical. The things we have to do to be practical, to be able to do any kind of measurement at all, right? So if I know what sigma is, that helps me out a lot because it takes away a certain, because if you look here, I have two elements of uncertainty here, don't I? In other words, how close is X bar to the actual population mean? How close is S to the actual population standard deviation? If I know what sigma is, then that takes away one element of uncertainty, right? So if I know what sigma is, then from then on, I can use the Z table. The Z table gives me the distribution of it gives me values for the proportions in the distribution, in the normal distribution, right? So that Z table is very convenient to use, right? It's going to be the most helpful version of these probabilities that I would have of how likely it is to get this low a number or that low a number when I take a sample. How far away am I? How far apart am I from when I when I take the sample standard deviation? How close am I to actually estimating the population mean? So Z helps us out a lot. The only problem now is that since I rarely know sigma over the square root of n, if I don't know sigma, well, then I have to use the standard deviation from my sample. So now I have to use the t distribution instead of the normal z distribution or normal distribution. You'll notice that with the z distribution, we have one table. Ours is broken up into two tables, really, because plus and minus, right? But it's really one table, right? With the t distribution, we have an infinite number of tables. And each table is different based on the sample size, right? Because the bigger the sample size is, the less likely we're going to get fooled by using the standard deviation instead of sigma, right? So the sample size, but now instead of using sample size, we use degrees of freedom. So for each sample size or degrees of freedom, one minus the sample size, for each degrees of freedom, I have a different t table. Now, since we don't want to have an infinite number of tables in the textbook, we instead just summarize all the critical values of t, the values of t for the different degrees of freedom that I need for 95% certainty, for 99% certainty, and for 90% certainty. Right? Those are the ones that I really need. I use over and over again. So I only really need a single number, just like for the z-score, where I know I use 1.96 for what level of confidence again? 95% confidence. And I use 2.58 for 99% confidence. And then I use 1.64, good, for a 90% confidence interval, right? Well, with the t table, those numbers, 90, 95, and 99, they're different for every different sample size, for every different number of degrees of freedom. Okay, so for instance, for 20 degrees of freedom, the 95% confidence interval might be something like, now I'm going to ask you to guess here, is it going to be a bigger number or a smaller number than 1.96? It's going to be a bigger number, right? Maybe it's 2.1, right? Why is it going to be a bigger number? Because since we're working with a sample, right, we're not as certain as to what the distribution is going to be for repeated samples. So we have to have a more conservative range than we would if we knew what the sigma was, this population standard deviation. And the smaller the sample size is, less certain we are, the bigger this number gets, right? And the bigger the sample size, the smaller this number gets, 2.1, 2.0, 1.99, 1.98, until eventually, when we have a really big sample size, it's almost exactly the same as the z-score. Because it's such a big sample size, we have a lot of certainty about it, right? So that's how we're going to use these tools now. First tool we have is calculating a confidence interval. Okay, so if we want to calculate a confidence interval, something's weird happening here. Let me just see if I can't get things straight here. want to calculate a confidence interval. Okay, that's better, I think. Okay, we want to calculate a confidence interval. Let's say that I have a population A. Whoops. And population A, and I take a sample from that population of 100 people. Okay, turns out my mean is equal to, let's say, 50. And my standard deviation from that population is equal to, let's say, 10. Okay, so now I'd like to know, well, I took a sample of size 50. I found a sample of size 100. I found a mean of 50. Now, what does that tell me about the population mean, mu, which is what I'm really interested in? Well, we can construct a confidence interval, right? So for a 95% confidence interval, right, I can say that my confidence interval is equal to x bar plus or minus my margin of error. What's my margin of error equal to? It's equal to my z-score or my t-score, right? Depends on my sample size and whether I know my sigma, which one I choose, times my standard error. Okay, so in this case, do I know the standard deviation of the population? No, I don't. I only know the sample standard deviation. So I have to use the t-score. And that t-score is for degrees of freedom equals 99, right? 1 minus sample size. Okay, so now how do I calculate this? First of all, I know x bar came out to be 50, plus or minus the t-score that I need for that sample size. Okay, so now on Blackboard for today's session, we have, in addition to these various other things, I also gave you the t-table. Okay, here's the t-table. Let me open it up. Okay, so we're only interested in that critical value of t, that value of t that represents our sample size. So the closest we have on this table is 100. So sigma, excuse me, the t-score for a 95% confidence interval is going to be equal to 1.984. Pretty close to 1.96, but not exactly 1.96. I'm going to call it 1.98. So I'm going to say 50 plus or minus 1.96 times my standard error. Well, what's my standard error equal to? My standard error is equal to sigma over the square root of the sample size, and that's equal to 10, right? I don't know what sigma is. I have to use S instead.
Square root of n.
Square root of n, right? Whoops. My pen's going a little wacky here.
1.984.
Yeah.
I'm sorry, you're right. I'm going to call it 1.98, yes. I'm sorry, say it again. Yeah, 99. There is no 99 on the table. So I just the closest number. Okay?
So what's the closest number?
Not was 99 was 100, right? If you looked at it, I'll go back to the table just so we're all clear. If you go down here, right, 100, this column represents 95% confidence interval, right? So 100 is 1.984. Okay? So I'm calling it 1.98 times my standard error. So my standard error is equal to S over the square root of n, because I don't know what sigma is, 10 over the square root of 100, which is 10, and that's equal to 1. So it's just 1 times 1.98. Okay, you lost me there? I lost you? So the standard error.
Can't see in the corner there.
Something going wrong up there? Oh, okay. I'll go back into the middle here. Okay. Hang on a second here. I'll raise this up and I'll go back into the middle. So my standard error is equal to, sigma over the square root of n, right? But since I don't know what sigma is, I have to use S. I have to approximate it with S over the square root of n, right? And that's equal to 10 divided by the square root of 100, which is 10. So that's 10 over 10 is equal to 1. Okay, it's equal to 1. So my confidence interval is going to be x bar 50 plus or minus my margin of error, 1.98 times 1 in this case, right? Pick a nice simple example. So what that's going to be? That's going to be 0.02 to 51.98. I'm sorry. I needed to get the value of t. Okay, here, I'll bring it up here again. Can you see it up there behind me? Right, so I took the closest number, which is 100. So I used 1.98. Okay? Right, so I still have to use a t-score, even though, like, if it had been 35, right? 35 and 40, I don't have 35 degrees of freedom, but it would be between 2.042 and 2.021, right? So it would be between those two numbers. So in that case, if I'm right in the middle between them, I would be tempted to average those two numbers, assume it's variable and average them, and call it 2.03. Am I running out of power there? Okay. Okay, good. Thank you very much. Oh, look how bright it got. Good spot. Okay, good. Good catch, yeah. So if we're between 30 and 40, 35, I would have said maybe 2.03, right? I would have made that judgment that it's halfway between them. Yes.
Can you remind us again, like, depending on the sample size, is whether we use the Z or T table?
Okay, first of all, number one, what determines whether you use Z or T is whether you use the legal limit here, like the speed limit, 55 miles an hour on the highway. The real legal limit is that it is, if you know the population standard deviation sigma, if you're told that, you use the Z-score. If you're not told that, and you have to rely on the sample, right? Doesn't matter if it's 25, 55, 100, 1,000 sample size. The sign is posted, use the T-score. And SPSS, when you do these calculations, SPSS doesn't, if you don't know the whole population, it always uses the T table. Even if it winds up being 1.9600001, always uses the T-score. Now, everybody knows that sign may say 55. How many people are really going 55? Right? Right. A lot of people go faster than 55, right? Most people go faster than 55. Same thing with statistics. If you're using the population, if you don't know the population standard deviation, but your sample size is large, okay, we'll talk about what large is, like 100. Look how close it was to 1.96. I would be tempted to say, sample size 100, it's going to be so close to 1.96. I even did it unconsciously there. You saw me write 1.96, right? Okay, so for the most part, if you got a sample size of 100, 200, for kind of exercises we're doing, you would just, if you're doing it by hand, you would just simply call it Z, you say the use a Z-score. In fact, a lot of textbooks will tell you, if you have a sample size over 30, just assume you can use the Z-score and use 1.96, right? What is it really, 30? 30 is 2.04. Still a little bit different. But I mean, for practical purposes, for most of the stuff you do in textbooks, like answering questions in textbooks, they usually say that 30, anything over 30 is a large sample. You can use the Z-score. I would be a little bit more conservative and say, maybe you really want to wait until you get to 100 and be closer to 100 or something like that for a large sample. So you really don't even notice the difference for the most part. Now, so you can look at it that way, right? Keep in mind, most of the time in real life, you're not going to be sitting down with a pen and pencil and doing these calculations. You're going to be using software. You're going to be using SPSS. You're going to be using SAS. You're going to be using R. You're going to be using any other kinds of professional software that do this kind of calculation. And they're always going to use, no matter, because it's not inconvenient for them to go to a T table. It doesn't add to the amount of work that they have to do or the complexity of calculation for them. They can use built-in calculations for the T table and never have to, even if it's a sample size of 1,000, right? If this table went to 1,000, it would be almost indistinguishable from 1.96, right? So we would use a Z-score. So the real rule is, if you only know S instead of sigma, you use the T-score. But on a practical basis, if you have a large sample size, you can use the Z-score, right? And for the most part, if the sample size is over 30, on an exam or on a homework, I would make the acceptable range for the answer wide enough so it would mark you correct if you used either one. Got it? Okay. If I had used 1.96, this would have been 48.04 to 51.96. Right? That's what I've gotten there instead. So I'd make the wide enough to make sure it accepted either answer, as long as the sample size were bigger than 30. But on a practical basis, when you do this in the future, not working with, like made up problems that we're working with, you might want to wait until you get a bigger sample size before you give up, like use the z-score instead of the t-score. Plus, to tell you the truth, I mean, use calculators, Excel, and stuff like that. It's just as easy to just go to the t-table, do a quick lookup, and use it. It's more accurate, too. Okay, so that's where we stand on calculating the confidence interval for a mean. Okay, so that aside, now let's move on to, now notice I didn't bother doing it for the standard deviation, right? Because we know that if we had been told the standard deviation, sigma, were equal to 10, then we would have had the same result for standard error is equal to 1, and then we would just use, by default, use 1.96, right? Would have been the same thing, except we wouldn't even bother thinking about the t-table. Okay, so now let's talk about a binomial variable, okay, which is kind of numerical because it's a proportion, right, a percentage. Okay, so let's say that tomorrow's the mayoral race tomorrow, right? Let's say that we do a poll, and the sample size in that poll is equal to 1,000. It's a phone poll, randomly selected phone numbers, right? And we ask people who they're voting for in tomorrow's election. So let's say De Blasio, and it would just for our purpose, we're saying De Blasio and all other candidates. Let's say that we find that out of that 1,000 people, that 600 of them are going to vote, say they're going to vote for De Blasio, 400 of them say they're going to vote for someone else. Okay. So now, what is the proportion of people that in tomorrow's election are going to vote for De Blasio? Right? Well, I don't know. I don't know what the vote tomorrow is going to be, right? Because that's going to be the whole population. It's going to be, I don't know, in these off-term elections, they get that big a turnout. Maybe 500,000 people or something like that might vote, right? Others, all others, like what's her name, Nicole, and what's his name, yeah, what's his name? Bo Dietl, right? Exactly, Bo Dietl. Yeah, now he used to be on radio, right? Bo Dietl. He was like an ex-investigator or something like that. But at any rate, yeah, Nicole and Bo Dietl, let's say, right? So let's say that the proportion of people that are voting for De Blasio tomorrow, we don't know that. That's P. We ain't going to know that till the election's over, right? But what we do know is P cap. What proportion of our sample is voting for De Blasio? So that's equal to 600 out of 1,000 people. Okay? Or 0.6. That's the proportion. Okay, so now, does that mean de Blasio is going to win tomorrow? No, this P cap here, our P cap, is only an estimate of what P is. What P is important, right? So now we want to know how confident are we that that less than 50% don't vote for someone other than de Blasio, right? How confident are we that that our 95% confidence interval doesn't include 50%? So we want to calculate a 95% confidence interval for P. Okay, and how will we do that? We do it the same way we did it with numerical variables. P cap, plus or minus, right? Well, should I use Z or T here? Look at that sample size. Yeah, we use Z. We're not going to bother. And this is almost universally true. Okay, when you're dealing with proportions, when you're dealing with binomial variables, before you do the test, your assumption is that all of these groups, whether it's vote for de Blasio, don't vote for de Blasio, vote for someone else, vote for this, vote for Nicole, all the numbers are going to be greater than 15, which means that you're always going to be greater than 30, and in most cases, way bigger than 30, right? So you're almost always dealing with large samples. So we're going to use Z, right, for proportions. Plus or minus times the standard error. Okay, so in our case, P cap is equal to 0.60 plus or minus our margin of error, which is Z, 1.96 times our standard error. Well, now we have to calculate a standard error. Well, this is a little bit different because we're not dealing with a numeric, with a common scalar numerical variable. We're dealing with proportion. We know from what we've learned before that the standard error is equal to the square root of P times 1 minus P over N, right? All of that underneath that square root sign. Okay, I don't know what P is. So what do I have to use instead? I have to use P cap, right? So P cap, that's equal to 0.6 times 0.4, right? 0.6 times 0.4 over 1,000, and then we take the square root of that whole thing. Okay, so let's go ahead and pull up a calculator and give that a try. Okay, 0.6 times 0.4 equals this, 0.24, divided by 1,000. Okay, it looks like a microscopically small number, but we got to take square root of it, right? For square root of a fraction turns out to be a bigger number. Okay, and it comes out to be 0.01549. You know, I'm gonna round that up, call that 0.16, make it a little bit more interesting. 0.016. Now, in reality, you could call it 0.155. I'll call it 0.155. In reality, it would be better if we don't round at this point, right? Why is that better? Because then what's going to happen, we're going to multiply it by a number like 2. Now we double the error that we multiply by a 2, 1.96 basically 2, right? Multiplied by 2, I've doubled the error that I made in rounding. If I square it, if I do that, it really magnifies the error, right? So it's better if you don't round until the very end. But on a practical basis, because we're doing this with pen and paper, I'm going to round this to 0.0155. I heard some moans. I was going to say 0.155 or 15 or 16, but I heard some moans. So I'm going to 0.0155. Okay, I'll call it 0.0155. Okay, so now I can calculate my margin of error. Okay, and in fact, if I go back here, it's actually 0.015, that whole number, times 1.96. 96 equals 0.030, so on and so forth, right?
I said
1.96, right? The z-score is 1.96. That's 0.0155, right? It's the number that we calculate. Okay, so now that number is my margin of error. That's the number I'm going to add and subtract. In other words, here, I'll put it in there. I'll actually write it in there so we know what it is. It's going to be 0.60 plus or minus 0.030364118, and so on and so forth. At this stage, I'm not going to do any other operation except add and subtract, so I'm going to just round it off to 0.03. Okay, so what is our percentage now, our confidence interval? Our confidence interval, we're 95% confident that the true proportion in this population that's voting for de Blasio is between 0.57 and 0.63, 57% and 63%. So we're 95% sure that it's bigger than 50%, 0.50. So it looks like he's going to win based on this sample, right? So now, had this come out to be 0.49 to 0.70, we wouldn't be 95% sure because it could be 50%, right? It was within. So the fact that 50% is outside the confidence. Today in the mayoral, I think in the mayoral race, you got to get 50% or there's a runoff, right? I'm not sure, right? So a lot of cities do that, right? I think New York possibly may be one of them, maybe not. Costs money to run elections. They probably don't want to do that. Okay, so at any rate, so that's how we calculate our confidence interval or proportions. Okay, everybody fairly comfortable with that? Okay, so that, now we're going to take that a step further. And that step further is comparing two proportions or two means, two populations. So we're only dealing with one population so far, one group. Okay, so now I'm going to take a look at two groups. population 1, I'll call it population A, and population B. Okay, this could be two ethnic groups, it could be two genders, it could be two countries, it could be two occupations. It could be anything that I could break up into two groups, right? That's categorical variable, the two groups, right? But we're measuring a numerical variable. Maybe I'm measuring blood pressure. So now I take a sample of size 100 from population A. Okay, and what do I get? I get X bar for population A. The mean for the sample I took from population A is equal to 100. Okay, and the standard deviation from this population is equal to 12. Now, population B, I'm going to take another sample of 100. It could be a different size sample. It doesn't have to be the same size sample. And now for the mean of that 100 people from population B is equal to, let's say, 90. Okay? And the standard deviation for this population is equal to 10. So now I want to compare the mean for population A to the mean for population B. If I want to know what the sample's mean is, I can just look at them. The mean for sample A is bigger than the mean for sample B, right? I'm done. I don't need to look any further. I'm done with the samples. But who cares about the samples, right? Because they're randomly picked out. What we really want to know if the blood pressure of population A is different than the blood pressure of population B, right? And since we don't know the populations, we're stuck dealing with this in chance. So we set up a hypothesis. We set up two hypotheses: a null hypothesis and an alternative hypothesis. Okay, and our null hypothesis is that the two means, mean for population A, is equal to the mean for population B. Our alternative hypothesis is that they're not equal, that they're different. In a sense, we do this backwards. Most of the time, we're trying to show that there's a difference between two groups, not that they're the same, right? But we set this up so it's formulated in a way that we start with the assumption that they're equal, and then we force ourselves to prove that that's not true. So then you can say that they're different, right? That's how hypothesis testing works. So now where do we go there? Well, first of all, what are the rules with these samples? What do these samples have to be? They have to be independent, and they have to be random. Because we want our sample to represent the population in each case, right? They have to be independent and they have to be random. Okay, assuming that that's okay, do they have to be normally distributed populations? Do the populations themselves have to be normally distributed? What do you think? Not a yes or a no. Remember the central limit theorem? Remember one of the things that the central limit theorem, besides telling us how to calculate standard error for the sample sizes, it also told us, if the population is skewed, right? Well, when you take repeated samples of the same size, turns out that if you take a sample size bigger than 30, that really smooths it out. So the samples are normally distributed. So the original population doesn't necessarily have to be perfectly normally distributed. So that's not one of the conditions. It doesn't have to be perfectly normally distributed, right? Because that's what the central limit theorem tells us, or part of what it tells us. Okay, so now I want to prove these two. So in order to prove these two, we know that if I start out with one of these being a mean and the other one being another different sample, well, most of the time what we're looking for is how far apart are these two things. So if I start out with mu for A, and then I want to know, mu for B, where my sample for A, the mean is here, but then I take a sample for B. How far apart are they? So in this case, A was 100, B is 90. The mean for B is 90, right? So given what our samples would look like from these two populations, how likely is it that I would get that big a difference, right? Well, what tells us how likely that is that we would get that big a difference. Well, this little tail down here, right? That's the probability that we would get that big a difference or more or less or more, right? In other words, only let's say that's 1%. Only 1% of the time would they be that far apart. So how do I figure out what that percentage is? The likelihood that they could be that far apart and really from the same population. Well, I calculate a z-score for the distance between the two of these guys, and or t-score if I don't know the standard deviations, right? Or and if it's a small sample, I calculate a z-score or t-score, the difference in standard errors apart. And I look to see if that area, actually I look at both ends, right? So whatever this area is, I'm going to double it so I cover it being bigger, one being bigger or smaller than the other, right? So I want to know what that area is so I can tell if it's more or less than 5%. The chances that I would get that extreme a difference that would make me say that they're not equal, but be wrong and that they actually are equal. Could happen, right? But we want it to happen very rarely, less than 5% of the time. So what we do is we calculate how many standard deviations apart that these two are. But since we're dealing with samples, it's really how many standard errors apart. So what we want is we want to know what t is. T or z, right? Depending on the sample size or whatever we know. T is going to be equal to the difference between the two means, x bar A minus x bar B, right? The difference between the two of them over the standard error. Okay, number of standard deviations apart is really what that is, right? So we know that if it's a big sample size, we want a difference that's at least, if it's a big sample size, we could have said z instead of t, right? And it is a pretty big sample size, 100 in each group. So we know we would want the difference to be at least my t-score, my z-score to be at least 1.96 for 95% certainty. It's better if it's bigger because that means they're even further apart than that. For 99% certainty, I would want it to be at least 2.58, right? The same numbers we use for the confidence interval, except that if it's a small sample, we got to use a t-table instead. Okay, so we're going to use a t-table in this particular example, just so that we keep everything with the 55 mile an hour speed limit, as we were talking about before. So let's calculate this. Okay, so t is equal to, I'm afraid I'm kind of getting towards the bottom of the screen there. Hopefully you can, maybe I can do something like this. Let's scroll up. Yeah, it'll scroll up. May make it a little easier to see. T is equal to x bar A minus x bar B, which is 100 minus 90 over the standard error. Now, how do I calculate the standard error? Uh-oh, this is a problem, right? When we were dealing with only one sample, the standard error was simple. We just used the standard deviation of that sample divided by the square root of n for that standard error. But now we have two standard deviations. So we have to figure out, well, which one do we use, right? Well, in fact, you kind of use both. Okay, now you'll find another document on Blackboard. I'll open that up now. I don't know where that's going. I don't know why that came up, but who knows? Sometimes these machines have a mind of their own. Okay, so under this document, Ttest Variations. Okay, when we compare the means of two populations, right? There are a couple of things that might happen. One is that the standard deviations of the two groups are equal, or the standard deviations are not equal. So what can we use as equal or not equal? Standard deviation is 12 and standard deviation here is 10. They're never going to be the same. Is that close enough for me to say that it's equal? What do you think? They're pretty close, right? As a general rule, if one is not twice what the other is, twice or more what the other is, if we're doing it by hand, assume that you can use you can assume equal variances. Okay, assume equal variances. If one of these was 10 and the other was 24, then assume that you should use unequal variances. Okay, in other words, instead of using the formulas on this page, use the formulas on this page. So in order to calculate the standard deviation now, notice that the top part is x bar a minus x bar b is real simple. But now we got to find out what we're going to use for the standard error. Here's our formula, x bar 1 minus x bar 2, and here's our standard error on the bottom. And you'll notice that there's another strange symbol, SP, times the square root of 1 over n1 plus 1 over n2. Well, that's pretty obvious. That's the two sample sizes, right? But what's this SP? This SP is a pooled standard deviation, basically a weighted average of the two standard deviations. How do I calculate that? I use this formula up here. The square root of n1 minus 1 times the standard deviation of the first group squared plus n2 minus 1 times the standard deviation of the second group squared over n1 plus n2 minus 2. Now just real quick over here before we actually do it on paper. N1 minus 1 is what? 99, right? Okay, times the standard deviation of group 1, right? Group A squared. Well, what's that? Standard deviation was 12. What's 12 squared? 144. Plus n2 minus 1. What was the sample size before? 100 also. 99 times the standard deviation of group 2 squared, which was 10, which is 100, over 100 plus 100 minus 2, 198. Okay? It's not as intimidating. Once you look at it, parse it that way, it's not as intimidating as it looks there. So I'm going to go ahead and do that calculation. I'm going to write it up here so that when I go to my calculator, that's to find the bottom of this equation is the standard error. Right? It doesn't say it there, but it's the standard error. But I need to find the pooled standard deviation to calculate the bottom of this equation. Okay, see it there on the, can you see it on the board there? In other words, we need to get that SP before we have to calculate SP from this formula and plug it in there to find out what our t-score is. Okay, so let's go ahead and do that now. Let me see. Okay, see if I can write small here. So now SP is equal to the square root of 199, with 99 times 144 plus 99 times 100 over 198. Okay, here comes my calculator again. I hate computer calculators.
Is that 99 plus times 144?
99 times 144 and 99 times 100, right? I want 12 times 12, the standard deviation squared. Standard deviation of the first group, first sample from the first group was 12. So 12 squared is 144. So 99 times, let me clear out the memory there. 99 times 144, right? I'm going to put is equal to, I'm going to put that into memory. Look at this. 99 times 100 times 100. As expected, it's going to be 9900. I'm going to add that to memory also. Clear? And then I am going to divide that by 100 plus 100 is 200 minus 2 is 198. So I'm going to recall memory and divide that by 198. Okay, and that's going to be equal to 122. So the top of that equation is 122. Now I have to find that square root. Square root of 122 is 11. What was the standard deviation of the first population? 12. By 12. What was the standard deviation of the second population? 10. The sample sizes were equal. What's the standard deviation we're going to use overall? 11, right? It's in the middle. It's a pooled standard deviation. By doing this, you make up for the fact that maybe the sample sizes aren't 12. So in other words, you really have to go through this exercise especially if one sample size is much bigger than the other sample size. So you get a weighted calculation for the sample size. It counts the one that's larger more. Okay, so in this case, it's 11.05, I'm going to call it. Okay, so that's 11.05 is our pooled standard deviation. Okay, so I'm going to calculate the second part of this, which is 11.05 over the square root of 1 over n1 plus 1 over n2. 1 over n1 is 1/100th. 1 over n2 is 1/100th. 1/100th and 1/100th is 2/100ths, or 1/50th, right? Or 0.02, right? So it's 0.02, clear. 0.02, right? 0.02, I'll take the square root of that, and I'm going to multiply it by the pooled standard deviation, which was 11.05, I think I called it, is equal to this. Okay, and that's what I'm going to divide into the difference between my two means. Okay, I'm going to clear this out. What's that? I'm talking, I'm not writing. I'll write it. I'll do it again, I'll write it. Okay. I'm running out of room there, is what the problem is. Okay, so here's my pooled standard deviation we just calculated was equal to 11.05, right? So now I have to complete this and fill in this formula over here, which is going to be equal to T is equal to 100 minus 90 over my pooled standard deviation 11.05 times what was it? The square root of 1 over 100 plus 1 over 100. Okay, I'm going to continue this up here. That formula is on, there's a document called Ttest Variations. It's on today's Blackboard files. Okay, so there it is over there on the board if you want to look up, take a quick look at it again. Yeah. It's T is equal to x bar 1 minus x bar 2 over the pooled standard deviation, which we just calculated up here, times the square root of 1 over n1 plus 1 over n2.
So it's going to be 2 over 200, right?
It's 2 over 200, which is it's 2 over 100. 1/100th plus 1/100th is 2/100ths. Right? 0.05, that's 0.02. Right? 0.01 plus 0.01. You can also look at it that way, 0.01. Okay, so now I'm gonna do the rest of that equation. So T is going to be equal to 10, the difference between the two means, divided by 11.05 times 0.02, the square root of 0.02. And the square root of 0.02 came out to be, I forgot. Okay, 0.02, square root of 0.02 is 0.01414. 0.0, actually, what was it, 0.1? 0.1, forgot it already. 0.1414.
Or 0.1414.
0.1414.
Where did I get a 0?
Okay, well, you won't get a 0 because, think about it, 0.1 times 0.1 is 0.01, right? So it's always going to come up, it's always going to wind up losing a decimal place there. 0.1414 is the square root of 1, the square root of that that sum. Okay, so I'm going to multiply this out. So T is equal to 10 divided by 0.1414 times 11.05 times 11.05. That's equal to 1.56. 1.56. So 1.56 is our standard error, and we're dividing that into 10. So t is going to be, value of t, the number of standard errors apart, is going to be 10 divided by 1.56. Okay, we're recording this, so you got a chance to see it again.
10 divided by 1.6.
Okay, I'm going to actually clear memory, put this in memory. Yeah, clear this and put 10 in here and divide it by 1.56. And it comes out to be 6 point, I'm going to call it 6.4. T-score is 6.4. What's the critical value of T? Imagine it's a big sample size. It is a big sample size, so we're going to use Z instead of T. What would be the value? What do you think would be the critical value of Z that we would have to exceed for 95% certainty? 1.96, right? And what did we get? We got 6.4. So they're so far apart, right? They're so far apart that the probability, right? Here's one mean. The other mean is 6 standard deviations away. It's way down here. It's so far apart that the probability that you would get these samples from two populations with the same mean is super, super small. Let's call it 0.0001. You could double that, call it 0.002, to make it what we call a two-tailed test, because we didn't say in the beginning whether population A was more than population B. We just said that they're equal or not equal, right? It's a two-sided test. So it doesn't, we're not prejudging. So in other words, the probability that we're 99.99% certain that these two means, the means of these two populations are different. What's our standard for being certain? Our standard is 5% chance of being wrong. We call that alpha equals 0.05. So as long as our probability of being wrong is less than 5%, in this case it's way less than 1%, we can say, no, they're not equal. We reject the null hypothesis and we accept the alternative hypothesis. Okay? There were a lot of steps getting to this point, right? Okay, so just so you know, I'm going to pull up the T table.
We rejected null?
We reject the null because they're so far apart that we can say with the level of certainty that we want that they're not equal. Okay, so now there's two ways I could do this. One way is the T-score is very large. Well, what T-score would I need to reject the null hypothesis? Well, let's see. For a sample size of 100, the T-score that would give me 95% certainty is 1.98. I can call that my critical value of T. That's the T value I need to exceed to say I'm 95% certain that these guys are different, because my T-score came out bigger than that number. Yes? I'm dinging here. No, what you say is I reject the null hypothesis and I accept the alternative hypothesis. Or another way that's very rarely you hear people say I reject the null hypothesis in preference for the alternative hypothesis. But probably more common, you say I reject the null hypothesis and I accept the alternative hypothesis. Well, what if my t-value, what if this number had come out, instead of being 6.4, what if t had come out to 1.4? Right? What's the value that it has to exceed for a sample size of 100 in order for me to reject the null hypothesis? The value it needs to exceed is the critical value of t for that sample size, which was 1.98, right? Did it exceed it if it was 1.4? No, it didn't. So they're not far enough apart for us to say that they're different. So we fail to reject the null hypothesis. That doesn't mean that we accept we accept the null hypothesis. We just fail to reject it. Okay, that's all we do. Okay, so now you guys are going to get involved. You want to take a quick break first? Okay, let's take a quick break. And then you guys are gonna get your pencils and papers out, and we're gonna torment you until you figure this stuff out.
Professor,
Yes.
you don't have, you're not recording, right?
Yeah, I'm recording right now. Why? You gonna say something to me I don't like? You gonna say something that's gonna embarrass us?
No, I'm
Hang
not
on,
mean,
hang
I'm
on a
not
second. I'll stop recording for a second. Okay, so we're back again now. Okay, let me get rid of this. Okay, so I'm gonna go back to that page I opened up before, that Word document that I opened up before, previously, and that's called lab exercises 1, 2, and I think there's a bit more paired samples. I think it's called. Okay. Okay. So here is the first problem that I have here is a single sample hypothesis test. Okay, it's on the first page there. A single sample hypothesis test. And in this case, I'm going to say we don't know. It's going to be the only difference between this first one, single sample t-test with known sigma, and single sample t-test unknown sigma. The only difference is that in one we know the population standard deviation, right? So we can use the z-score. In the other, we don't know the population standard deviation. And since it's a small sample, we have to use the t-score, that one, right? So we can get away, even though it's a small sample, we know what sigma is, so we can get away with that. But let's do the second one, where we don't know it and we have to use the t-score. Okay, so now we take a sample from a population, 1, 2, 3, 4, 5, 6, 7, 8, 9. The sample size is 9. We don't know what sigma is, so we have to calculate the mean and the standard deviation from our sample. Okay, so we're going to do that together now. I'm going to use Excel because it's going to be a little bit easier. In fact, I may even have this one.
What's the name of that file again?
It's called Lab Exercises 1, 2, and Paired Samples. Okay, it's in today's stuff. And there's a bunch of data sets there. And in the data sets are a bunch of examples, like single sample test. I'm going to open up the one that says the Excel file for now. And if I'm lucky, it's the same numbers as we have here. Well, hopefully it's more than luck, but right? So yeah, there it is, right? There is our sample that we just looked at here, right? So I want to calculate a confidence interval for that. So how am I going to do that? Well, first I got to calculate X bar, right? Then my mean for the sample. Then I got to calculate S, my standard deviation for the sample. Then I got to note what is the sample size, right? And now to calculate my confidence interval, right, I have to take X bar. I'm going to go down here with this. X bar plus or minus. Okay, now I need to use a t-score here, right? Because I don't know what sigma is. T times my standard error, right? Well, that means I got to calculate my standard error. How do I calculate my standard error? Well, my standard error is equal to my standard deviation divided by the square root of my sample size. Okay, I got to use my standard deviation of my sample. So everything I need to know is here. So I'm going to give you guys about 5 or 10 minutes to calculate X bar, the standard deviation, the sample size, standard error, and then together we'll calculate the confidence interval. Okay, by the way, if you go onto Blackboard, there's a file called number1 single sample test.xlsx. All you have to do is right click on it, tell it to save it to your desktop. You might have to navigate a little bit, get onto the desktop. Or you could just, there's only 9 numbers, you could just type them in to Excel. Or you can do it with a calculator for that matter. I see squinting going on. Oops. Does that help? Make it any clearer? I tell you what, let's close. Can somebody in the back there close the kill the light? That should help things a bit. I'm going to pause the recording. Okay, so in SPSS, I'm going to open that same file. Open, data. Okay, it's called the same name. It's on my desktop. It's on Blackboard for you guys. And let's see, where is it? There we go. The data sets. And number one, single sample test.sav. Okay, so I'm going to open this up. So here's my data. It's the same data I had before, right? The same numbers I had before. Now, what I'm going to do, I'm going to go to Analyze. I'm going to go to Compare Means, right? Because the t-test basically is comparing means. Okay, and I'm going to go into one sample t-test. Why? Because I'm going to compare my single sample to a mean from a known population. Okay, so here's my sample. There's my values for X. I'm going to move it in there. And in the test value, I am going to put in the value that I had for the mean for that other population. What was it again? It was an average of, the mean for that other population was 6, right? So I'm going to go ahead and I'm going to calculate my t-score. I'm going to click OK, and it's going to do exactly the same calculation that we did before, right, by hand. And it's going to calculate it. And what t-value does it get? It gets 3.976. Well, what did we get? Anybody remember? Yeah, pretty close, right? Oops, I got the wrong one. Let me find it. Let me find it. Where is it? I got 3.97, right? 3.97. Got pretty much the same thing. I rounded a bit, I think, at some point. Okay, so now let me go back to SPSS. And I'm going to look at the output table that SPSS created. Here's the output, that SPSS output table. It calculated the t-value is 3.976. Now, if I have a t-table handy, and it told me that I have 8 degrees of freedom, if I have a t-table handy, I can look up the t critical for 8 degrees of freedom. Turns out it's 2.304. And I can say, well, my t-score I calculated for my sample is greater than the critical value of t for that sample size, so I can reject my whole null hypothesis that these means of the two populations are the same and say that I accept the alternative hypothesis that they're different. But now SPSS actually gives you more information. If you look at the next column, it says significance two-tailed. Well, what is that? That's the area that's under the normal distribution when you're 3.976 standard deviations away from the mean on either side, right? In other words, this is the probability you would get that extreme a value for t if the two populations were the same. Translate that into, that's the probability you would be wrong if you reject the null hypothesis. That's alpha, exactly. So in other words, if you want to be 95% certain, your level of acceptable error is 5%, right? That's what you call your alpha error. So you want to make sure your probability of being wrong is less than your acceptable limit for being wrong, which is 5% or alpha. In other words, that the significance, or p-value we call it sometimes, is less than 5% or less than alpha. So in this case, it's 0.004, which is way less than alpha. So that confirms the t-test, the t-value, is bigger than the critical value of t, and the significance, the p-value, is less than 5%. Both of them tell you the same thing: reject the null hypothesis. Okay, so now let's take a look at a two-sample t-test. Okay, so now let's see. Okay, so now two-sample t-test, as we saw before, gets rather complicated, right? Because now with a two-sample t-test, we did a sample calculation before. With a two-sample t-test, let me find my right page here. With a two-sample t-test now, we now have to use either this calculation, pool the standard deviations, or this calculation if we're assuming unequal variances, right? Now, notice that the calculation, if you assume unequal variances, is actually a little simpler, isn't it? The t's value, the number of standard deviations apart, the t-score apart that you have to compare to the critical value, is the difference between the two means, x bar 1 minus x bar 2, over the standard error. And the standard error, instead of having to calculate a pooled standard deviation, well, the standard error is equal to the standard deviation of the first sample squared over the sample size, plus the standard deviation of the second sample squared over the sample size. You take the square root of that, no pooled standard deviation. It's actually a little simpler, right? However, look at this. You can't just add up the samples and say that that's the degrees of freedom, as you did before. Now, when you assume unequal variances, unequal standard deviations between the two groups, now you have to use this ugly formula to calculate the degrees of freedom. Nobody uses that formula. Most people just say, I'm just going to take the smaller sample and subtract 1 and call that the degrees of freedom. Very conservative approach, very simple approach. So for us, if it were 9 and 9 with the two sample sizes, you just stick with 8 as the degrees of freedom. Now, rather than do this right now, I'm going to ask you guys to open up an SPSS, download, and open up in SPSS the file on Blackboard called, let me find it here, called number 2 sample ttest.sav. You should be able to download that, drop it on top of your desktop, not the Excel one because then we would have to go through all the calculations. You want the 2 sample ttest.sav. I'm going to do that myself. I'm going to open it up and then open it up in SPSS. So I'm going to open it up in SPSS and then I'll pause for you guys to catch up. Open, data, and then navigate to the desktop and look for the 2 sample ttest.sav. Okay, and here it is. It's males and females. One variable is gender, males and females, and it's calculating the difference between two values, two samples, one for males, one for females, from a population of males, population of females, and the sample size for each is 9. So I'll wait for you guys to catch up with me and open that file. Okay, just on Blackboard, right-click on it, say save linked file as, drop it on the desktop, and then either double-click on it or open SPSS and open, navigate to the desktop and open. Right? So 2 sample t-tests now. So if I go up to Analyze, Compare Means, it's not 1 sample t-test. Now it's independent samples t-test. There's 2 samples, 2 independent samples, one for males, one for females. So I open this up and I put the test variable values, whatever it is, and I put gender into the grouping variable, split it up into those 2 groups. Now notice it asks me to define those with the numbers that's represented, which was 1 and 2. Kind of an inconvenience. You would think since there's only 2 numbers there, for $1,000 the program would figure that out. But like I said, IBM, their stock is doing great too, I think. But at any rate, that's all. I think Microsoft doing good. But at any rate, who knows? So at any rate, let's say, okay, everybody's stock is doing great. All these companies' stock are doing great because they're all like salivating over the tax breaks they're going to get. So at any rate, let's say, okay, Okay, and see what we get if they get them. What's that?
The OK button's kind of like I'm not able to hit OK after putting the two.
Oh, you know why? Let's see. Let's go to. I'm going to go there. Analyze, compare means, independent samples t-test. Did you put in the grouping variable? The define groups
For gender?
For gender. Click in define groups. You have to put in the 1 and 2 in there.
For group 1, you put
1. For females, you put 1, and for males, you put 2. It wants the numbers. The reason why it does it is because it'll only work with 2 samples, right? It's 2-sample t-test. Only work with 2 samples. You could have a situation where, let's say that the categorical variable was ethnicity. You could have 10 different ethnicities, listed in that variable. But with a t-test, you only can compare 2 at a time, right? So you would tell it, oh, I want to compare 3 and 8, right, to let it know which ones you want. But since it's only 2 values in there, you would think it would know by itself, but you have to tell it. That's why it wouldn't light up the OK button. So you click the OK button. Let's see what our result is. Our result is that the t-score, now ignore that first part. See that Levine's test for equality of variances? Don't worry about that for right now. So look at this. Look at the next part. What is the t-score in that top line? 2.184, right? That's my value at t for the difference between these two means. What did I say my critical value at t had to be? Anybody remember anymore? Let's go back to the table. For 16, the degrees of freedom equal 15. Where did I put it? I must have closed it. Not there anymore. Okay. The degrees of freedom equal 15. It's equal to 2.13. And the critical value of t is 2.13. My calculated is 2.18. It's bigger than my critical value. So what does that tell you? We can reject the null hypothesis because they're far enough, the t values is far enough apart that you can reject it. If it were smaller than 2.13, we couldn't reject the null hypothesis.
So we have 2 groups, each with 9
Right.
units. What if the 2 groups had different numbers?
It would still be if it's equal variances, it's still n1 plus n2 minus 2.
And if it's not equal variances, like
Then you have to do that ridiculous calculation, but in reality, you just take the smaller sample size, subtract 1. So you would call it a sample size of 8 degrees of freedom. Okay? Okay, so what's the other way we can check to see if we can reject our null hypothesis? Look up our probability of being wrong, our p-value. And what is it for this particular analysis? It's 0.044. There's 4.4% chance we're wrong. What's our acceptable level of tolerance for error? 5%. So that also tells us we can reject the null hypothesis. Okay, both of them go hand in hand. Notice that the t-test was very close and the p-values were very close because they go together, right? And that's always going to be true. If the t-test says you can reject, the significance of p-value is going to tell you. But the nice thing about SPSS is it tells you precisely what the probability is that you could be wrong. So before, when we did it previously with that one sample test, there was like only less than a 1% chance of being wrong. Now we see that the chances of being wrong are like almost 4.5%, right? So that kind of gives you a little bit more information. But usually, for the most part, we're looking at the bigger picture. Can I reject the null hypothesis? Or can I reject the null hypothesis? In this case, you can reject the null hypothesis. Okay? All right? So just so you know, if you look over here at those 2 boxes I told you to ignore for now, Levine's test for equality of variances, that is an actual statistical test that you can use to determine whether you should assume equal variances or unequal variances, right? Rather than just take my word for it and say, oh, it's not double what the other is. So the way that this works is that the top line represents the calculation for t if you assume equal variances. The bottom line is the calculation for t if you assume unequal variances. Okay, so now we decided to use the top line because we assumed unequal variances, equal variances, because they were so close, right? They weren't, one wasn't double the other. Well, what if we use Levine's test for quality of variances? The way it works is you start off with the null hypothesis that the variances are equal. So you start off with the top line and you only use the bottom line if you reject that they're equal. Well, what tells you if they're equal or not? Well, this calculation F is a statistic, and the probability that goes along with it of being wrong if you reject the idea that they're equal is 0.245. Again, statistical tests, usually we're looking at a level of tolerance for error of 5%. Since this number is bigger than 5%, we fail to reject the idea that they're equal, so we stick with the top line. If this had been less than 0.05, we would have said, I'm going to say they're unequal, the variances are different, and use the bottom line instead. Let's take a look at the bottom line. The t-score is basically the same. Actually, it might be different in an extra decimal place or two, right? Degrees of freedom is equal to 16. How do we get that? N1 plus N2 minus 2 is the degrees of freedom. It was 16, not 15, by the way. I subtracted an extra number, right? Well, okay, the t-score here is the same, but the degrees of freedom are different. Look, it came up with a really weird number for the degrees of freedom. Why did it get such a weird number? Because if you assume unequal variances, SPSS actually calculates that funny formula, and it comes up with a weird number for degrees of freedom like that, not a whole number. So that's why you see that there. And in fact, the significance is a little bit different because your degrees of freedom are different, right? So you wind up with a slightly different result. In both cases, you could have rejected the null hypothesis for this data set. Okay, so I'm going to ask you to do another one. Data set number 3, 2 sample t-test number 3. Okay, that one says 2A. 2A, 2 sample t-test unequal variances, .sav. So we're going to open those up in SPSS. Okay, so I'm gonna,
Two samples there.
2 sample test. Okay. Compare means, independent samples t-test. Okay. Whoops, what did I do here? Open, data, 2A. There it is. I think it's the same data, except we're assuming unequal variance. No, I think it's different data. Analyze, compare means, independent samples t-test. Values, gender. Now notice you don't know if they're equal variances, unequal variances. I just named them that way, right? But you don't know what they are until you actually do the analysis. Remember to put in 1 and 2 for the grouping variables. So you're going through the same steps as you did before because you don't know if they're equal or unequal yet. You haven't done the analysis yet. So I'll wait for you guys to catch up to me. I'll go back up here again just so you see what I did. Analyze, compare means, independent samples t-test. And then when I hit that, it comes up with a variable box. I put the values in it, a numerical variable in the top box. And I put the categorical variable, in this case gender, in the bottom box. And then I have to define the variables, tell it it's 1 and 2. And then click OK, and it does the calculation.
That's on my screen. The same info pops up, but in a different order. Is that
I'm sorry, what's that?
the same on my screen? The same info pops up, but in a different order. Like the group stats box is above the independent samples test box. Is that bizarre?
No, probably just a version, difference of versions.
Okay.
Okay, so this is the output that I got. Hopefully it's something similar to yours. The first thing I look at is equal variances assumed versus equal variances not assumed. Our null hypothesis here is that the variances are equal unless we get a significance less than 0.05. So we reject that idea and accept that they're not equal. Well, in this case, the significance came out to be 0.013, less than 0.05. So instead of using the top row, as I did before, now I'm going to use the bottom row. But again, the values are not all that different. And most of the time, you won't see them that difference anyway. So what's the t-score? The t-score is 2.51. What's the degrees of freedom? The degrees of freedom are 10.152. If I go to my t-table, I can see what my critical value is going to be for t, for 10 degrees of freedom. Okay, that's what SPSS calculated using that wacky formula. Okay, let's see, what did I do with it? I keep closing it inadvertently. Here we go. So for 10 degrees of freedom, we need to exceed a t-score of 2.28 in order to reject the null hypothesis, 2.228. Okay, so let's see what our t-score is. Our t-score is 2.51, right? So can we reject the null hypothesis? Yes, we can, because we got a t-score bigger than the critical value of t for that sample size. And so that means when I go to my significance for that second row, it should automatically be less than 0.05, the other thing that lets us reject it. And in fact, the probability of being wrong if we reject our null hypothesis is 0.031, about 3%. So again, that tells us we can reject our null hypothesis. I use the second line because in this case, let me, matter of fact, I'm using an image of this. Let me go back to SPSS and show you the actual table. Nope, got the wrong one. Where'd it go? Here's the output table. If you look now, go back here. This is a different data set than we used before. The variability, the standard deviation for males is 1.0. The variability for females is 2.7. Can I say they have equal variances? No. In fact, if you look at the way SPSS calculates it, it uses the Levine's test for equal or unequal variances, and it looks like this. Oops. Oh, sorry. Don't need that. I need the other version of it. Where'd it go? There it is. It uses the Levine's test for variance, which you see this box, you start off with this box right here. Levine's test for equality of variances. Notice that there's a big tall line here to separate it from the t-scores. Okay, this line tells you whether to use the top row or the bottom row. If the variances are the same, use the top row. If the variances are unequal, are soon to be unequal, you use the bottom row. Okay, so we already said because they're so different, we would probably use the bottom row because one is more than double the other. In Levine's test, you actually calculate the probability of being wrong, making that assumption, and you want it to be less than 5%. So these four boxes, these two boxes, tell you whether to use the top row or the bottom row. You start with the assumption you're going to use the top row, unless the probability of being wrong, if you reject that, is less than 5%. In this case, it's less than 5%, so that tells you, oh, reject that, use the bottom row. That's why we're using the bottom row. And that's why I used the t-score. I looked up a critical value of t for critical value of t for 10 degrees of freedom. But in any case, the probability of being wrong if we reject the null hypothesis is only 3%. So this tells us we can reject the null hypothesis. Okay? We're going to do one more.
Anything less than 5 is rejected.
Anything less than 5%. Significance less than 5%. Okay, we're going to do one more, which is a little tiny bit different. There's another file there called, let me find that folder. If it's still open. There it is. I think that's it over there. There's another file there called 3 paired samples.sav. Okay, so I'm going to open up that file in SPSS. If I can find SPSS again, there it is. Open, data, and this one is going to be 3 paired samples.sav. Okay, and now we have 9 people who were in the study. Person number 1, person number 3, 4, 5, etc. They were given a drug. For 2 weeks, they took a placebo or they took a drug. It doesn't show which order. They probably randomized the order. But person number 1, this is his score when he took the placebo. This is his score when he took the drug. But it's the same person. So we're not really interested in what the value was when either one of these. We want to know what the difference is for that person when they took the drug and when they didn't take the drug. So for this person, when they were on the placebo, the value was 10, whatever it represents. When they took the drug for 2 weeks, it was 8. But both these values represent the same person, right? So we're really only interested in the difference for each person, right? And what we want to demonstrate, so what would that be? Difference for this first person would be 0. For the second would be 2. For the third would be 4. For the fourth would be -3. For the fifth would be 2. For the sixth would be 1. For the seventh would be 6. For the eighth would be 1. For the ninth would be 3. We want to know if we can say with 95% certainty that the drug made a difference. So we want to prove that the average difference is really different than 0. So when you're doing a paired sample t-test, what you're doing is you're subtracting all the values from each other, getting a single column, and then comparing it to there's no difference, right? What kind of test is that? That's a single sample t-test. A paired sample t-test is really a single sample t-test, except the value that you're comparing it to, instead of a different population mean, is the value 0, that there was no difference between the drug and the placebo for the average person. Okay, so how do we do that? We go up to Analyze, this Compare Means, Paired Sample t-test. And we tell SPSS which 2 groups are we pairing? We're pairing the placebo. It's really the same people. The values when that person took the placebo versus the value that we got when that person, the measurement we got when that person took the drug. And we click OK, and it does our analysis for us. And our paired sample t-test tells us that the mean difference was 1.556, gives us a standard deviation. The standard error is just the standard deviation divided by the square root of the sample size, which was 9. 2.6 divided by 9 is 0.9 roughly. And it gives us a confidence interval, and it gives us a t-score. So now we need to compare that t-value to the value that we would need to exceed to reject the null hypothesis. And what's the null hypothesis here? The null hypothesis is that the mean difference is equal to 0, or the mean difference is not equal to 0, right? So in order to reject the null hypothesis that the mean difference is equal to 0, I have to have a t-value that's bigger than, what are the degrees of freedom? Sample 9 people, right? There were 18 readings, but it's really just 9 people, right? 9 people minus 1 is 8 degrees of freedom, which was 2.304. So our t-score has to exceed 2.304. Does our t-score exceed 2.304? No. So what do you say about our null hypothesis? We failed to reject our null hypothesis. Okay. So now we failed to reject our null hypothesis. Is there more evidence here for doing that? What's the probability of being wrong if we reject our null hypothesis? It's 12.2%. Is that less than 5% chance of being wrong? No. So again, we failed to reject our null hypothesis. The t-score and the significance go together. It's a paired sample t-test, right? Because they're paired samples. The same person measured twice. In other words, if you went to Weight Watchers and we measured your weight on day 1 and on day 30, right? We're not going to compare you to some other person. We're going to compare you to yourself. So if we take 10 people, we want to know if Weight Watchers works. We might take 100 people, and we might put them on the program for a month. We might say, okay, we're not interested in what your weight is when you started. We want to know what your weight is when you started versus your weight when you stopped, when you ended, right? 30 days later. So you have 2 numbers for each person. You have before and after, but it's the same person. What you're really interested in is the difference, which is a single number. So what are you comparing that number to? Then their weight didn't change, 0. So we're testing whether the average weight loss is equal to 0, the null hypothesis, or the average weight loss, the difference between the two, is not equal to 0. That's called a paired sample t-test. It's really a single sample t-test, but you're comparing, instead of comparing your single sample to some other known mean, you're comparing it to no difference between group A and group B, right? Before and after. More appropriately before and after, because it's the same person. Okay? So I think we beat this to death enough for today, right? See a lot of glazed eyes.
So this data suggests that the drug isn't effective at all?
Exactly. No, the drug, now you can't say that. The null hypothesis is that there is no difference between the drug and the placebo, right? There's no difference between the different, I can't say that the difference is not equal to 0. Right? Difference is equal to 0, null hypothesis. We can't reject that. But we just say we failed to reject the null hypothesis. We failed to prove that there's a difference. That's different than saying the drug doesn't work. We haven't proved that. What we've done is failed to prove that it does work. Right? There's a subtle but really important difference there. Right? Because we're not trying to prove that it doesn't work. We're trying to prove that there is a difference. Right? So if we wanted to prove that there isn't a difference, that would be a whole other technique. And really, you're probably never going to want to do that anyway. You're always trying to prove that it works. That an intervention, that a difference, that there's a population mean is different and so on. Okay. All right. So I'm going to put up a homework assignment, and I'll put up more examples. This will be on Blackboard, and I'll put up some videos, some recordings of us doing this, so that you can reference those as you do the other problems, the homework problems. Okay. What time is this class at? 3:40 or 3:50?
3:40.
3:40. Okay.
We
I
always
never-
go to three.
I never know because 110, 3, who makes these numbers up? I mean, what's wrong with 1 to 3? I mean, the night school, they started on the hour. I don't
Can I
know.
ask you a quick question about
Sure.
the mulligan?
Yes,
For question 2,
yes.
if we rounded, and we would still get that answer wrong, maybe you don't know off the top of your head the question, but.
Yeah, let me look it up. Uh,
When the T is bigger,
Come on. Wake up.
T is